All right, Chem 20 IBs. It is the third part of stoichiometry, and we're going to be talking about stuff in solution. This is aqueous solutions, and we're going to be dealing with moles per liter. Way back to the solution unit, chemical amount per liter. So you'll find in these reactions and using the stoichiometry and the unit analysis, we will need to build a fraction unit. So moles of one substance on top and liters on the bottom. Sometimes maybe you'll just be solving for moles. Sometimes you'll be just solving for liters. And we'll maybe get to some mixed problems by the end of the week. But for today, we're going to be solving for moles per liter. The good thing is the way you solve these problems are just like gas and just like mass. Write the reaction, write down what you know. Don't forget the mole ratio. Solve for the unit the question wants you to solve for. Now, the reactions for these are just a little bit trickier because we might have some acids and bases to think about. Okay, so let's look at this one. What volume of 14.8 mole liter ammonia solution is needed to completely react with phosphoric acid to produce 1 liter of 12.9 mole liter ammonium phosphate, the only product? Okay. Well, there's a lot going on here. So let's write out the reaction. We have ammonia, NH3. Okay, it's aqueous because it's got concentration. All right. Needed to react with phosphoric acid. Okay, we could look that up in our data booklet. Remember the big chart of acids and bases? If you're a giant nerd like me, you have that memorized. And it says we make one product, ammonium phosphate. Ammonium is NH4. Phosphate is PO4, 3 negative. So we have 3 ammoniums for every phosphate. Now we have to balance this. It looks like if I check out this here, we have 3 groups of ammonium, and that means we have 3 nitrogens. If I put a 3 here, I think it works out. And you might say, oh, but wait, Mr. Z, there's 3 hydrogens here, but 4 hydrogens there. True, but don't forget about those 3 hydrogens there. So it does, in a way, work out. Okay, so we have a balanced reaction. Now we have to write down what we know. So it's asking for volume of ammonia. Perfect. Okay. And it says we have a concentration of ammonia, and the concentration is 14.8 moles per liter. Now, I'm going to do that annoying thing where I write down what belongs to what. That's 14.8 moles of ammonia per liter ammonia. Okay? And I have 1 liter H3PO4, and I have 12.9 moles per liter H3PO4. Moles per liter H3PO4. You'll see in a second, it's really important that you label what liter belongs to what, because it's easy to see a liter variable and forget what thing it belongs to, and then you're going to have wrong unit analysis. What am I forgetting? Well, I'm comparing my 2 reactants. It's not even talking about this. Okay, so I need the mole ratio between those 2 substances. Okay, perfect. Mole ratio, just throwing it out there. Oh, I don't know. Let's go 3 mole ammonia for every 1 mole of phosphoric acid. Okay, all right. So that's all of my variables. All of my things. What is the question asking me to solve? It's asking me to solve liters of ammonia. Now here, if you didn't label this liters of ammonia, you might just say, oh, I'm being asked to solve for liters, and you might see that liter there and think, oh, that's what I have to start with. But I actually have to start with liters of ammonia right there. Okay. So my final answer, I need to have liters of ammonia on top of a fraction. Okay, it can't be on the bottom. So if I'm going to start with 14.8 moles per liter, I need to flip that. So I have liters of ammonia on top, and 14.8 moles of ammonia. Now I did that to get the liters of ammonia on top. If you flip something, the variable follows the entity. So I don't just move 14 to the bottom and have 14.8 liters on the bottom. No, the liter and goes to the top, and the 14.8 mole goes to the bottom. Okay, so I'm already winning. I've got the liter of ammonia on top. Now I have to use my skills of unit analysis to cancel out everything else. We got to get rid of moles of ammonia on the bottom. Oh, we've used that. That's gone. Where do I have moles of ammonia? Right there, mole ratio. That's how important mole ratio is. 3 moles ammonia for every mole phosphate. Okay. Use that up. Now I got to get rid of moles phosphoric acid. Oh, it's in the concentration. 12.9 moles phosphoric acid for every liter phosphoric acid. Okay. So moles cancel. I have liters of phosphoric acid on the bottom. How do I get rid of that? I put liters of phosphoric acid on top. Pow! Solved it. Okay, got everything solved except for liters. Multiplying everything out, top 3 times 12.9 times 1 divided by 14.8 times, well, 1. I got a syntax error because I pressed a weird button there. 1 second. 3 times 12.9. And I'm going to divide that by 14.8. I get to 3 sig figs, 2.61 liters. Okay. So this was a solve for 1 unit. The next question, we're going to solve for moles per liter. A little bit different. Okay. So this says sulfuric acid completely neutralizes potassium hydroxide. Blah, 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 blah. Okay, now you might see we have a volume in milliliters. That's okay. Check is the other volume in milliliters. Good. We don't have to change anything. It's probably going to work out. In fact, if we had volume in milliliters and it was asking to solve for volume, like this other question, we would just solve for milliliters, not liters. It's all good. Okay. First step, let's write out a reaction. Sulfuric acid is H2SO4. Okay, we've got some sodium hydroxide. All right, now this is a neutralization reaction. So this is a complete reaction. So all of the sulfuric acid reacts with the sodium hydroxide. Now I'm going to erase this, but sulfate in this case is hooked up to 2 hydrogen ions. So this is a neutralization, but it works like a double replacement. That sodium comes in and kicks out the hydrogen. And so you wind up with, so the sodium goes over to the sulfate. You wind up with a sodium and a sulfate. But sulfate's 2 negatives, sodium's +1. So we get Na2SO4. And that's going to be soluble. So the other product is the hydrogens come over here. What happens to them? Do you get H2OH? No, that doesn't make any sense. The hydrogens are acting like a metal, and the hydroxide is 1 negative. Okay, so you get water. In a neutralization reaction, you get water, and it's sometimes easier to write water as HOH. Now we have to balance it. It's true that there are 2 hydrogens in sulfuric acid, so the hydrogens are not balanced. We need to put a 2 there. The other thing that's not balanced is the sodiums and now the hydroxides. Putting a 2 there balances the sodium, but it also means we now have 2 hydroxides. And if we look, we have 2 hydroxides right there. So it all checks out. So neutralization reactions are probably the trickiest of the double replacement. If you notice you have an acid and a base, think about splitting whatever's attached to the polyatomic off, and then that becomes one of the products with the metal. It may not help you. You might have to practice it. Okay. All right, let's write down what we know. We have 10 milliliters of acid of H2SO4. Okay. Reacts with 15.9 milliliters of potassium. Oh, whoops. I did this whole problem with sodium instead of potassium. I'm sorry. It's still going to work, but potassium is 1 positive. So I just have to switch this out. So we need K2 right there. If you were a little confused with what I was doing, I'm sorry, but it still works out. Potassium is 1 plus, sodium is 1 plus, same difference. Okay, we have 15.9 milliliters of potassium hydroxide, and it gives us the concentration of potassium hydroxide, 0.1050 mole per liter. Now, let's not be lazy. Let's write down what that belongs to. And we're comparing, because we want concentration here, these two. Oh, I need a 2 there to balance. And my mole ratio then is 1 mole sulfuric acid over 2 moles potassium hydroxide. Okay, so sorry about that mistake with the sodium-potassium thing. All right, anyways, what is this question asking me to solve? Now, it's a little bit trickier because it's asking me to solve moles per liter. That's moles of KH2SO4 per liter H2SO4. So I have to build a fraction. I have to make sure moles of H2SO4 are on top and liters of H2SO4 are on the bottom. So let's start with the mole. And the mole H2SO4 I'm going to start with is from the mole ratio. I teach this in Chem 30. If you are doing a solution stoichiometry, probably the first thing you should start with is the mole ratio to get the mole of the substance on top that you need. Remember, we need mole of that substance, and we have it right there. Now we should probably put liters of that substance next. Or we could cancel out moles of potassium hydroxide by using the concentration. So we have a bunch of different ways to go. Let's get rid of the moles of potassium hydroxide. Perfect. Okay. Now we have liters of potassium hydroxide on the bottom. And we need liters of potassium sulfuric acid on the bottom. So the last step, we can probably do a double. So let's go 15.9 milliliters of KOH, and the liter part cancels. And let's put 10 milliliters of potassium hydroxide on the bottom. Or sulfuric acid on the bottom, 10 mils of sulfuric acid on the bottom. Okay, and if we look, the millis cancel. And we get moles sulfuric acid for liter sulfuric acid. So what I teach in Chem 30, a way to do these problems, if you're solving for concentration, is a pattern. It goes mole ratio, concentration, volumes. And you'll see when we do titrations, probably early next week, you can solve titration problems if you're solving for concentration pretty much the same way. Mole ratio, concentration, volume. Okay, so that's it for this lesson. I'm going to give another lesson tomorrow with more solution stoich, and you'll have that day tomorrow. To finish up the assignment that's due this week. And we'll start something fresh on Thursday. Okay.